I got it. And now I'm kind of overthinking it. Like everything else you know is going to add to that noise, even though it probably would not have originally, you know? It's fine. She's young. She doesn't know. She's a tiny little freshman.
All right. Let's pick up where we left off. Bootstrapping. All right. Bootstrap standard errors gives us a way to calculate confidence interval pretty easily once you get it going in R. And it's really nice because of all of these properties. All right. So what we're going to do is quickly review our bootstrapping and what we do. That awesome. See how close we are. Got it. Hey, we'll just do that. We'll get it. All right. This has already been on presentation, but we're going to drive it home. All right. So the first thing we do is we have our vector. All right. First thing we're going to calculate is get our observed test vectors. All right. So in this case, we're going to use our x bar, our mean, because we want the standard error of the mean. So we're going to get our observed x bar and save it. Do we have to save it? No, not really, but we're doing it because it gets us ready for doing randomization tests. Our randomization tests are going to be very similar to how we do bootstrapping. Slight changes, but we need the observed in those cases so we can get p-value. All right, so then we have our observed test statistic. We're going to save it, and then we're going to do our loop. And this is our bootstrapping loop. So our bootstrapping loop is going to do a few things. Actually, before we do that bootstrapping loop, we're going to create an empty vector. All right. And in this case, we'll just say R mean for randomized mean. All right. Once we have that randomized or that empty vector, now we're going to do our bootstrapping. All right. So our bootstrapping loop. Bootstrapping loop, what we start off with is that 4i to 1,000 or 10,000, right? And then what we're going to do is create a randomized vector. We're going to sample with replacement. And save the vector. In this case, I will call it rvec. So rvector. That's our sample with replacement. This is our bootstrapping. Then we're going to calculate, and we're going to save x bar of rvec. And we're going to save this as r mean. We're going to use the bracket, and we're going to use I. All right. So we did our bootstrap sample. We calculate our test statistic of interest, our mean, and we're going to save that value into our empty vector, or what was once an empty vector. And then we're going to, once we have that, then we're going to repeat this loop. We're going to repeat it a large number of times. All right, what's large? Anytime you do this, you start off with a small number. Say start off with 100, just to make sure it's going to work and it's going to work quickly. And then you're going to typically do like 10,000 samples. All right? How many you actually need to do depends on this vector itself. Depends on that original vector. If the original vector is only 10, we can figure out how many different ways we can get. Right? 10 to the 10 gives us how many different combinations we get. Ideally, our sample should be at least as large, maybe larger. But if we have, let's say, a vector of 1,000, well then a sample size of 10,000 might not get us all possible combinations or get us close to that. So maybe we have to do 100,000 or 1,000,000 perhaps. So you can see how things really get out of control very quickly. And if you started with 1,000,000 samples or 1,000,000 bootstrap samples, maybe it's going to take you 2 days to run. Sure, you don't want to sit here at the computer for 2 days waiting for it to run. So we do this, and now when we repeat it a large number of times, we actually have this R mean filled out. Once we do, now we look at 95% time. So we do our quantile function of R mean, where we are taking 0.025 and 0.97. And that'll give us the upper and lower cutoff that'll capture 95% of all of our values in that R mean vector. All right. This is the basis of our bootstrap. All right. Questions? All right, so why is bootstrapping so useful? Because we don't make any sort of underlying assumption of the distribution. All right, we can have non-normal data, and we can still calculate a confidence interval. If we have skewed data, we can get a 95% confidence interval, and that interval will reflect the underlying distribution. It will be skewed. All right, if we're normally distributed to begin with, then our confidence interval will reflect that normal distribution. And that's kind of what we say here, is our parametric confidence interval is when we use the t, where we calculate our t statistic, and then we use that and multiply it by our standard error. Well, if we're already normal, then our confidence intervals, the parametric confidence intervals, will be the same as our bootstrap confidence interval. And that's a power. In some cases, I don't even do the parametric confidence intervals. I just do all bootstrapping. All right. Second big utility of this is that we can calculate a standard error and a confidence interval for basically any statistic. We're using means, but we could do variances as well. No problem. We can get a confidence interval of the variance. We can get a confidence interval of our t statistic. We can get a confidence interval of our z. It doesn't matter. We can do it for any statistic. And I told you, one of the things that we use it for in our research is to do a confidence interval of a percentage. Percentage is just one number. Use all of our data set. You know, in one case I had, almost 200 individuals in a sample. Percentage was one number. And people would say, well, you can't calculate a confidence interval from one number. And I'd argue, yeah, you can. You can use bootstrapping, no problem. Just generate our own distribution or our own random data to get that confidence interval. We already talked about the underlying distribution, how if we're skewed, our confidence intervals will be skewed, and that's a good thing. All right. And the other useful thing is that the bootstrap means will be centered on our sample. And that is the central limit theorem. That was on slide, I don't know, I guess 14. I assume it's still slide 14. But it's the idea that as we take repeated samples, the mean of that randomized vector is going to approximate the mean of our actual sample. All right? So what we're going to do is do this as practice. Right? We're going to set our seed to 2015. We're going to generate a random data vector, okay? Call it dat.x, and we're going to round it Yeah, so we work with hundredths place. So run that, and then what I want you to do is kind of look back at the notes, at the example that's in here, and try to generate a confidence interval. 95% confidence interval for that vector. All right. I say calculate standard error as well. You can do that. Just kind of a drop on that point. But go ahead and do that, and then as you do that, I'm going to get it on my R so we can kind of work through it together. And again, just kind of talk about what each step is doing in our chunk. And in theory, if we did it correctly, everyone should have the exact same vector and everyone should have the exact same confidence interval. So, get my R studio. How's it going? Kind of follow it through. The more generic we can make it, the better. Because that means that when you copy and paste in different chunks, there's fewer items that we have to update. All right?
that was going to be our empty vector, and then I tried to write in there, and it said, I don't know where this vector is. Is that a 1 or an I? Get it? That's something. Here's this a little different. Maybe. Let's see.
All right. Should we take it? Do you need a little bit more time? I give you a little bit more time. As I wind this up, and then what we will do is take a look at my script. All right, so here's mine. Set seed, ran it. All right, and the thing that I did was I tried to get it generically since we are working with the mean. All right, so I did mean.obs for observed mean. I said it would calculate the mean of dat x. All right, then I created my empty vector and I called this R mean for my randomized means. And then I have my bootstrap loop, and that's what this is. So I said for I in 1 to 10,000, all right, I sampled this dat.x vector, and I'm sampling it with replacement. So this is the basis of bootstrapping. All right, this is bootstrapping. Sample with replacement, and I'm going to save it as rvec. And then with rvec, I'm going to calculate the mean of that vector, that bootstrap sample, and I'm going to save the mean in R mean, which was that vector that we just created, that empty vector. And I'm saving it in row I, so that's what our square brackets are. And then this will keep doing it over and over and over until I get 10,000. All right? So you can see, R mean, I've got 1 to 10,000 here inside of my vector. Now, calculate the standard error. All that you have to do is take the standard deviation of that mean, of that R mean. That is our bootstrap standard error, and I just kind of clarified it down here with the output. So note the standard deviation of a bootstrapped a standard deviation of a vector of bootstrapped means is the bootstrap standard error. So it's important, if you're going to report the standard error, you should say this is the bootstrapped standard error, and that distinguishes it from normal standard errors. All right? So I calculated it as 0.224. I think everyone probably would have calculated it the same. Did anyone get a different number? Your number's different?
No, I fixed it.
How'd you fix it?
Because I did standard deviation instead of the standard error.
Okay. Okay.
And I guess I didn't click set seed first before I ran it.
Yep. So maybe you use the standard error function to calculate it, and that's not quite right. Because once we do our bootstrapping, then the standard deviation is the standard error of the mean. All right? So we did do our bootstrapping to get that collection of means. Whereas if we didn't have that collection of means, then we have to do the whole standard deviation over the square root of our sample size to get the standard error, or the approximate standard error of the mean. So with bootstrap samples, all we have to do is take the standard deviation and get that standard error, that bootstrap standard error. My 95% confidence intervals go from 3 to 3.88. That's mine. All right? Did you guys get anything different? Yes? No? I can get something different.
actually. It is slightly different. So every time I run it, I'm going to get a slightly different value. I think it's probably easier to see my standard deviation or the bootstrap standard error. So every time I run it, I get a slightly different number. And the reason we're getting a slightly different number is because we are doing a randomization method. We're sampling with replacement. So every time we do this, we can get a slightly different answer. But if I set the seed, then we have one randomization method here. And then if I run it again, so I ran that chunk, and then if I immediately run this chunk, then everyone should get the exact same standard error, the exact same confidence interval. All right, questions? Questions? All right, so here's our lectures. I have a data set, leaves.csv. All right, so in leaves.csv, open it up. This is just a practice. We're going to check our answers and go through them in lab. So it's 2 columns. I've got length and width of, let's say, leaves. I'd say these are in maybe millimeters. All right. So what I'm going to ask that you do is to calculate 95% confidence interval, bootstrap confidence intervals of the length and bootstrap confidence intervals of the width. And then what we can do is compare these to a parametric bootstrap as well to see how these values compare to how our bootstrap confidence intervals compare to a parametric bootstrapped interval. Right? That's for length. For width, I'm going to add, since I said we can do it with any statistic that we want. So I'm going to say let's try bootstrapping and do a standard deviation. See what the 95% confidence interval of the standard deviation is. Maybe we're interested in variation and variance. So for length, we'll do the mean. For width, we'll do standard deviation. And we'll do this in lab. So you can kind of work on it before then. So again, just to kind of reiterate, as I write these codes, I try to do it generically. Try to have things generically. So if I copied and pasted this chunk into a different chunk, how many values do I have to change? Well, I'm going to have to change det.x. That's changed. And then I have to change it there. And then everything else stays the same. So I'm just trying to make it easy for myself, because I know when I started out doing this, it was always, how did I do this again? Right? So I had one file that had some useful functions, and when I open up a function, I have it generic, a generic function. If you don't believe me, I'll show you. Let's see. Make sure I didn't queue on this. No. Function script. Access denied. Let me go through my key drive. Documents, ASU. Here it is. Function scripts. So I've got setting paths, standard errors. I got a bootstrapped mean function that we'll get. I've got sign test, G-test, goodness of fit, all of these things. I've just kind of made a script that has everything in it. So if I'm working in a markdown document, I could very easily then copy and paste it, and everything's generic. So we'll get these permutational ANOVA tests. permutational t-test, and I kind of specify where we change it. So everything's just kind of generic. All right, so did that. Power of a test. All right. So beta is your type 2 error, right? Power is 1 minus that beta, right? It's a probability of actually rejecting it when our null is false and our alternate is true. So you can kind of look at actual and test to kind of see these relationships. So if our actual null hypothesis is true, then our test will either fail to reject it, just 1 minus alpha, or we'll reject it at some alpha level. That's our type 1 error rate. If our null hypothesis is actually false and we need to reject it, then the power is that probability, 1 minus b. And what we always want is to have a test that has high power, that actually rejects our null hypothesis when it should be rejected. So how do we improve our power? Well, it comes down to some general rules. First up is the type of test. So a parametric test is a test that assumes normality. All right, assumes normality of our data. We have those assumptions, and anytime we do those tests, we have to check that normality assumption. In general, these parametric tests have more power than a non-parametric test. So a non-parametric test doesn't make that assumption of normality. We use it often, or we can use it when we violated our normality assumption. And you'll see it. So if we had our choice, we always want to try to go for that parametric test because of the higher power. All right, but if we use a lower power test and we do find significance, then in all cases, we're going to get significance for the parametric test. So it's one of those things that maybe we violated our assumption, maybe we didn't, and you chose to run this non-parametric test at the cost of power. If you find significance, then there is really no benefit to try to do a parametric test. You found significance, it's there. The non-parametric test had enough power to detect that difference. What about some other things? What if we know that we're normally distributed, all right, we're running this parametric test, but we still fail to get that significance. We still fail to find significance. How do we increase the power further? Well, we can focus on the difference of mean. So if we're comparing two groups, obviously the more different those means are, the higher the power. But a lot of cases, we don't have control over that. All right, we can't tell a leaf, hey, you need to get bigger so I can find significance. That doesn't work. What about variation in a population? All right. So if we increase the amount of variation we have in our population, we actually decrease our power. It becomes harder for us to detect differences because now instead of looking at comparing means and errors that look like this, where, yeah, we can detect differences between these, we're looking at something like this. Where that major overlap is making it harder for us to actually detect the difference. All right. Do we have any control over this, the variation? Not really. Unless it's like caused by measurement error, we really don't have any control over that. But what we do have control over is the sample size. So increase your sample size, you're going to increase the power of the test, no matter what. So if you do a collection of 10 leaves and you're comparing leaf lengths between two species and you don't get a difference, you don't get a significant difference even though you know there is a difference, increase your sample size. That'll make it have our test, that'll give our test a higher power. Is sample size too much of a sample size a thing? Yeah, it can. So we see it all the time. You'll see it in the news. These scientific studies that say, oh yeah, eating bacon is bad for your health. All right, how do they come up with that? You ever wondered? I mean, look at butter and margarine. I can't believe it still happens. They say butter's good for you, and then butter's bad for you. No, butter's good for you. No, butter's bad for you. How do they do that? How do they come up with that? Eggs is another one. Eggs are good for you. No, eggs are bad for you. Eggs are good for you. Eggs are bad for you. How do they do that? Well, it all comes down to your sample sizes, and it comes down to significance. So with a large enough sample size, you can detect very, very small differences. Very small effects. So yeah, eating bacon, one piece of bacon a day may increase your mortality rates 0.001%, but if you have a sample size of 1 million people, that is significant. And then you can publish it. All right? So that kind of goes back to statistical significance versus biological significance. They can be different things. All right, so one of the questions that always gets asked, and it's related to power, but one of these things that I always get asked is, how many samples do I need? All right, you're getting ready to do a research project, and your advisor says, well, how many samples, how many replicates do we need? And then they say, go ask Dr. Negevich. All right, none of them have had the class at this point. So they're all like, okay, I'll go ask them. And then they don't know anything that I'm talking about. I'm like speaking a foreign language to them. All right, but you guys are gonna know it. All right, so when Cody comes in and says, Dr. Strength asked me to know how many shells do I have to measure? I'm gonna say, go back to this presentation. All right, so the sample size. How many samples do we need to know? Well, if we're going to calculate our sample size, right, we need to know the power that we're striving for. We need to know the estimated means, so the mean difference, and we have to have a measure of variation in our populations. Do we know that? Cody, on your shells, do you know what your average sizes are? Do you know how much variation that you're looking for? Not. No, and who does? I mean, who really does know that? You don't. So then it comes back to me and I say, measure as many as you possibly can. All right? Measure as many as you possibly can. But it becomes important if you're doing, let's say, a clinical study. Because now you're trying to work with humans, let's say a drug study. All right? We don't know how an individual is going to respond. We don't know how the sample of individuals is going to respond. But this starts up the preliminary study. We're going to do 100 people, 100 in a placebo group, 100 in our treatment groups. We're going to get our means. We're going to get our variance. And we know what our target power is. So then based on that preliminary study, we can go back to the institutional review board and say, okay, based on these figures, I have to increase my sample size to 1,000 individuals. And now, we have a sample size that we can proceed with. All right? And everyday work around here, around this department, it's probably very unrealistic for us to do anything like that. So as a rule, then, when we're dealing with sample sizes, measure as many as you possibly can and go from there. All right? So yeah. Sample size for an experiment. That is their usual question. All right, so what we're going to do is stop here because we have the bootstrapped examples. So in these next 10 minutes, you can work on the bootstrapping of the length. So bootstrapped confidence interval of the length of those leaves, and then we're going to do bootstrapping of the variance just to demonstrate that we can do it with any statistic. You can work on it, get it working, and then what we'll do is when we start in lab, I'll give you like another 10 minutes. And then we'll walk through it again. Once we finish, we will move on to our next part, which is actual hypothesis testing. We're going to start with just 2 groups, or start with 1 sample. Is our sample mean equal to some value? And then probably on Wednesday, we'll probably get to our second group. At this point now, we have, with these bootstrapped examples, the homework that's posted. That was posted last week. It's going to be available. So what we'll probably do is let you do this homework in the last half of lab. So then on Wednesday, we can have it due. If you run into any questions, we can answer questions in class on Wednesday. All right? find you this afternoon. So those of you at home, if you run into errors or problems, please email me before our lab, and we'll get them addressed.
Are we setting a seed for the leaves?
No, you don't have to. No, if you want to set your own seed, you can. So any time that you run it on your own, it'll work. But no, we don't have to set the seed. That'll just kind of demonstrate how close everyone is. And I do think we'll get ranges very close to each other. There will be some variation, but we'll get them close. All right. All right, I'm going to end the stream. We'll pick it up this afternoon.